per sample are not going to meet it. So, and we say that okay, now we are going to use 7 bits per sample. So when we go to 7 bits per sample, this resolution will now be 0.1 instead of 0.2, thus giving the user an added advantage that by using 7 bits we are being able to improve the resolution a lot. So when we quote anything, when we develop proposals, when we develop designs, engineering designs, then these are the calculations which are very important, so that you do not waste the quality room which is provided by these numbers. And this is not only related to quantization, this happens in all engineering domains, that the numbers you choose have their effect on quality, and we have to ensure that we choose such numbers which give the maximum benefit to the system design. Right, so let's look at another question. It says to determine a bitrate, so we have to find the bitrate, and the resolution in a sampling of a signal. We have been indicated there is a signal which is being sampled with a dynamic range of 1 volt. So the signal is not given, but the dynamic range is provided to us, which is 1 volt. If sampling frequency is 20 samples per second, so we are given Fs. Fs is provided as 20 samples per second, and we are using an 8-bit analog to digital converter. So we are given another information that this quantizer is of 8-bit per sample. And the third question which is asked is what maximum frequency can be present in the signal. So you see that now this question is not exclusively related to quantization. This is taking an input from the sampling scenario as well, as we have seen that the sampling frequency is now in the picture as well. What maximum frequency F max is also being asked. So this is an interesting question because it is now combining both the quantization process as well as the sampling process. So let's look at these questions. Let's address these questions. So part A, where we have been asked to compute the bit rate. The bit rate of an analog to digital conversion will depend on 2 factors. So first of all, we have to see that the rate, the units for bit rate will be bits per second. We call it BPS as well, bits per second. So that's where the kbps, mbps comes from. The internet devices we take or the mobile data we get, so they are measured in that sense. So this gives us the speed with which the bits are being produced or streamed. Now to calculate bit rate, there are 2 factors which are important. One is Fs, that in 1 second how many samples are being taken of an analog signal. So if we are taking too many samples a second, this will increase the bit rate. So higher the Fs, higher will be the bit rate. And then the second factor is that once you have a sample, then how many bits per sample we choose. So if one sample is taking 2 bits per sample, then it will have some bit rate. But if we have 10 bits per sample for the same scenario, then it will increase the bit rate. So having more bits per sample also increases the bit rate. So although connecting this with the previous discussion, that if we increase the quantization levels, then it increases the quality. But at the same time, now we are seeing that if we have more quantization levels, it means that we will be needing more bits per sample and we will be needing more bit rate. And the cost of bandwidth is in terms of bit rate. So therefore, the quality and the bit rate cost has to be adjusted so that we can have an optimum solution. Anyway, coming back to the question. So if we are to calculate bit rate, then the bit rate formula is very simple: fs multiplied by bits per sample. In the question, we were provided with fs as 20 samples per second, and we were told that this analog to digital converter was a 8-bit. So 8-bit times 20 gives us a bit rate of 160 bits per sample. So 20 samples are being sampled every second, and each sample is now converted into 8-bit stream. So total bits per second will be 160 bits per second. Part B, we were asked to calculate the resolution, and resolution formula we have been seeing repetitively. That's delta is dynamic range divided by L minus 1. Dynamic range is 1 divided by 2 raised to power 8, because it was an 8-bit converter. So 2 raised to power 8 minus 1, and you solve it, you get 0.0039 volts per level as a quantization step, or quantization resolution. The third question which was asked was that if fs is 20 samples per second, what can be the minimum frequency that can be sampled through the system? And we know the Nyquist criteria, as f max has to be less than or equal to fs by 2. So 20 by 2 is 10 hertz. So it is easy to note that maximum frequency present in the signal can be 10 hertz, up to 10 hertz. Now let's look at the last question. It asks, consider a signal. We are given a signal xt as sine 2 pi f1t plus sine 2 pi f2t. So there are two sinusoids being added here, and this is being sampled at an unknown sampling rate. So sampling rate is not known, fs is unknown. The resolution of its quantizer is given as 15.686 into 10 to the power minus 3 volts per level. The bit rate out of the system is 1600 bits per second. So we are given the bit rate as well. Part A is find out bits per sample of this ADC and its sampling frequency. Part B is we have to find out whether the system will work properly if f1 and f2 are 100 Hz and 200 Hz. And part C is that if f1 is 50 Hz and f2 is 100 Hz, will it be possible to reduce the bit rate from 1600 bits per second if we do not want any aliasing, and that the resolution is not worse than this value, 31.5 into 10 to the power minus 3 volts per level. So now let's look at the solutions. So part A, we were asked to find out bits per sample and fs, and we are given with the resolution and the bit rate as 1600 bits per second. So for the signal xt as two components of sine being added, the maximum value can be 1 plus 1 as 2, and the minimum value can be minus 2. So the dynamic range will be 2 minus minus 2 is 4 volts. So we can calculate the resolution as dynamic range over L minus 1, and we are given the resolution and we are provided the dynamic range. So we can calculate the value of L, and after simple calculation we get the number of levels as 256 levels. So now we know the number of levels, we know the bit rate, and we have to find the bits per sample and fs. So we take the log of 256 to the base 2, we come back as 8 bits per sample. So now we know that the number of bits required in this case is 8 bits per sample, and using the formula of a bit rate, which is fs into bits per sample, bit rate was given as 1600, and now we know that 8 bits per sample are used, so we can calculate fs as 1600 divided by 8 as 200 samples per second. So this, now we know that the system is sampling the signal at 200 samples per second. Part B was that if f1 was 100 Hz and f2 is 200 Hz, and now we know fs as 200 samples per second, whether the system will work properly. So this is a very simple scenario. We see that the maximum frequency in the signal is 200 Hz, and we know that the maximum frequency has to be less than or equal to fs by 2. In this case, this condition is not being met. If f2 is 200 Hz, then the minimum frequency should have been 400 samples per second in order to sample both of these signals correctly. But because this criteria is not being met, fs minimum is 200, fs is 200, and f2, which is fmax in this case, is 200 Hz, and the Nyquist criteria is not being followed. There will be aliasing and the sampling will not be happening correctly. In part C, we were provided with two frequencies. F1 is 50 Hz, F2 is 100 Hz, and the resolution was provided as 31.5 × 10⁻³ volts per level. And we were asked to try and see whether we can reduce the bit rate. So we see the bit rate is fs into bits per sample. So if you want to decrease bit rate, then either fs has to be reduced or bits per sample has to be reduced. In this case, fs is 200 samples per second because we have the maximum frequency is 100 Hz. So fs minimum will be fmax into 2. 2 into 100 is 200 samples per second. So this is the minimum fs we can have. So as we have seen that it was already 200 samples per second, so we cannot reduce fs from 200 samples per second, otherwise there will be aliasing in this case. So we are left with a bits per sample option. So using this delta value, delta is equal to dynamic range over L minus 1, we place the value of delta and we place the value of dynamic range. We find out L, which comes out to be 128 levels. So for 128 levels, now we know that this requires 7 bits per sample. So 7 multiplied by 200 gives us 1400 bits per second, which is slightly less than 1600 bits per second as was in the previous case. So although we tried to, so we had two options of reducing bit rate, fs or bits per sample. We could not reduce fs, but we were able to reduce bits per sample, and thus we are successfully able to reduce the bit rate from 1600 bits per second to 1400 bits per second. Right, so with this we conclude chapter number 1. What we have learned in this lecture is that we have looked at quantization levels, quantization steps, dynamic range, quantization resolution, quantization error, bits per sample, and we have done some numerical exercises to understand the quantization and its associated topics. We have also discussed the overall effect of sampling frequency and quantization resolution on the bit rate or the data quantity. So now, as I mentioned, that chapter number 1 is concluded. So specifically for this section, you have for this lecture you have to read section 1.4, except the subsections mentioned here, and these are the examples which you are expected to go through, and all of the end of chapter problems except 1.15 and 1.16. These you have to do before we meet in the live lecture for week 2. So best wishes, and we will be starting chapter 2 from lecture number 5. Thank you.